So basically last day we at the end of the class we have formulated the list of steps that we have to follow if we try to create a multi-layered perceptron, and we have also taken a use case with an example, a small example. We have seen that if we do the forward parts in the step 1, then how the output we are getting, and based on that how the backward pass will be done, like the back propagation actually, how the error is calculated, and finally based on the delta function calculation and all, how the del w, that means the changes of the weight, will be calculated, and finally we will get the updated weight which can be used in the next iteration, right? So up to this we have done. So now what we can do, we can start with an example. Like this is a numerical example we have seen. Now let's deep dive into the code, and let's see how we can write the code for the same. So as you can see here, like we are using a data set named irisdata.csv. What this iris data? This iris data is a data of some flowers, and this flowers has 4 features. So based on that, we have 3 different type of pattern we can see in the data set, name given as iris setosa, iris versicolor, and iris okay, something more is there but it's not yet visible. Maybe if we do like head, say for example 20, maybe if we run this, you will see, yes, iris virginica. So these are 3 classes, and the classes I have written in the form of 0, 1 and 2, but you can define your class in a different way. For example, see, this 0, 1, 2 is representing the class number only, does not have any numerical importance. So there are another way of representing this data set in which particular class this pattern will be. Like you can consider 3 columns representing the class. For every class, 1 column. Like this output can be ordered as 3 columns. Output 1, output 2, output 3. Just assume like that. So if the data is from iris setosa, say output 1 will be 0, other will be, sorry, output 1 will be 1, other will be 0. If the input is iris versicolor, then maybe output 2 will be 1, other will be 0. Or if the input is iris virginica, then maybe output 3 will be 1 and other will be 0. I mean, one of the output is 1 and the other will be 0, based on which particular input. Okay. So that is another way. So anyway, so let's start. Let's see how we can continue. So the code that you can see here, this is the exactly same code that basically we have, it's a reflection of the equations that we have seen in the PPT. For example, here I have considered a class MLP. That's why all these are considered as a function. Sigmoid is a function, sigmoid derivative is another function, train is another function within the MLP class. And what this init function does, this init function acts something like, you can say, a constructor with respect to object oriented programming language. You know what constructor is. A constructor actually used to initialize the variable of the class by some data. In the same way it is done. In case of constructor in Java, you have written use this pointer. Here we use self. That is the only difference. Otherwise, it is same like a constructor. So you can easily see that it is representing the input size, hidden size, and output size initially. What is this? This is representing the number of neuron will be present in the input layer, hidden layer, and output layer. That's all. And then we have a initialization of the weights here. If I just make it little more bigger for you, you will see it's a weight initializations. And as I told you that when we start training and neural network, we don't have any idea what will be exactly the weight. So we start with an arbitrary value, and in general it is between 0 to 1. So this np random.randn is basically doing the same of this particular size. So based on the input, based on two layer, like this weight input hidden, this is representing the weights between input layer and hidden layer. Now what will be the dimension of the matrix? That will depend upon the number of input layer, the number of neuron in the input layer and number of neuron in the hidden layer. As simple as that. According to mathematics, already we have seen. Similarly, we have to go for bias. We have to go for weights for the hidden to output, as well as wait for the bias for the hidden layer. But definitely there will be no bias in the output layer. So in this way, you see the weights are initialized, and these weights will be definitely updated by the equation that we have seen. And you see it's a simple sigmoid function which is 1 by 1 plus e to the power minus x. The same thing is done here. So the exponential is, we have a function is exp in the numpy package, that you can use np.exp, which will give the exponential of minus x, where x is the input of the sigmoid function. Similarly, just like sigmoid, we need the derivative of sigmoid also, because we have to back propagate the error. And if you recall the back propagation equation, the list of equations that we had, there was a delta calculations and all, and there was a use of derivative of the sigmoid function. So this sigmoid derivative will be used during the backpropagation time. That's why it is also required. And we have already seen in previous classes that this calculating a derivative of sigmoid function is very easy. That's simply nothing but the function multiplied by 1 minus the x multiplied by 1 minus x. That's all. Anyway, so now let's come to the train function. This train function is used to naturally train that particular model. So if I go for train the model, what I need? I need the data with which I will give the training. Like if I want to teach you, I must have some data with me. That means some subject knowledge or something like that. That basically I am going to teach you. So in machine learning, the data means a data set having list of inputs and corresponding output, right? So the list of input is this X train, and the corresponding list of output is the Y train. What is epochs is? Epochs actually, you will see, like, just try to visualize in this way. Like, assume that your teacher is teaching some subject to you, or maybe you have started learning some subject from the very beginning of the book. So at a stretch you learn everything of the subject, like everything in the sense, assume that you have read the whole book. But reading the whole book only once may not be sufficient for you for a very good learning. Say for example, learning with respect to say 0.95% accuracy. Like 95% accuracy means after reading the book, you will able to solve 90%, 95% of the problem correctly. And if you want to reach in that particular level of accuracy, maybe only once is not sufficient. Maybe you have to read the book twice or thrice or many more times. So basically, we can assume like you are reading the book at a stretch once from the beginning till the end. Then again you have started from the beginning, and again you are basically reading the same thing. So it's a sort of revise that we call. So this is what actually is called the epoch. The epoch means the number of times that basically we revising that particular um data set, and we already know the learning rate. So the parameters that we are passing in the train function, I hope it's clear. Now let's see. We have just written here losses equal to a cell within bracket open close. It's just creating a list, a blank list, where I'm going to store the loss. Loss means actually the difference between the correct value and the predicted value. Okay. So as I told you that you are reading the book at a stretch once, then twice, then thrice, like that. So in the same way, that means it's a for loop. It's a loop. So that's why I have a loop here. Maybe you can use for loop or maybe while loop, doesn't matter, but has to have some loop. So that's why this loop is there. And you see, if you come within the loop, so for a particular epoch, say for the first time or second time, whatever, as I'm saying that you are starting reading from the book. So with respect to the machine learning model, what you will do in a particular epoch, you are feeding the input to the model, right? Which is basically we conventionally say as a forward pass, and that's why this forward pass is written here. And if you see the equations of the forward pass, it is nothing but, you see, it is just multiplying the data, the x train data, with the weight, which is nothing but, if you recall the equation, wtx, right, plus b. So this is w and this is x. Since it is np dot is written, so automatically wtx will be done. So this is representing the wtx plus bias, this one, and this wtx plus bias is the linear summation. On top of this, what we apply? We apply the activation function, right? That's why you see we basically pass the whole thing. The result of this is passed as a parameter within the sigmoid function, which is written here. So once we will get output from this sigmoid function, it is nothing but the output from the network. So that is what the output, but it is a hidden output. It's for the first layer, like input to hidden only. It happened. Now hidden to output has to have done. In the same way, you see it's done. WTX plus B, but now it is the W means hidden to output layer weight. That's why weights hidden output and hidden output we just calculated here, and then added with the bias of hidden layer, and then again passed to sigmoid function. So actually it's written in a single line. If you closely watch this line and try to understand the smaller components, you will understand that what's exactly happening. Maybe when you will write program, you can break it down into 5 statements if you find it is good for you. There is no mandatory that you have to write everything in one line. Anyway, so as a result, now we are getting result from the output layer. That's why output came. Now, if you again recall what we have done, Once we get in the output layer, we started calculating the error, and that error is back propagated with the help of delta function, and then the weights were updated. During this time, this calculating error, calculating delta function, and going back is a part of back propagation, right? And that's why you see after forward pass, this back propagation started, where we started with error calculation. And this is nothing but the delta calculations over here happening. I'm not going in much detail of exactly what function is doing, because it's very simple, you know, execution of the equation that we have just discussed in the last class. So if you just put the equations in your left somewhere in one side and put this code in the other side, you will easily map. You can easily map what's happening, right? So once this error calculation, delta calculation is done, see, I must have two delta calculation, two delta. I mean, one delta for the hidden layer and one delta will be for output layer. And that's why you see there is a two separate delta here, delta output and delta hidden. This delta output will be required to change the weight of hidden to output layer, and delta hidden will be used to calculate the weight of, I mean, calculate the weight change of input to hidden layer, right? And once the delta calculation done, with the weight updation started again by the same equation, but here you see it's written as weight hidden output. That means the weight of hidden to output layer plus equals to, it means like in C also you have seen A plus equals to B. It means A equal to A plus B. So here weight hidden output plus equals to B means weight hidden output equal to weight hidden output plus. So it's basically at a stretch it is adding the previous weight hidden output with the delta W that we are going to find out. What is the value of delta W? The delta W will be this. The hidden output multiplied by delta output multiplied by learning rate. If you're not able to recall, just put the equation in your side somewhere in your hand, just we have discussed in last class, and see this line. You will clearly understand, I'm sure. It's not a very rocket science I've written here. Simple, just executing the equations that we have derived in the similar way. So basically we have not here written delta W separately, then W equals to W plus delta W. We have not written into two line, rather I have written into single line, that W equal to W plus delta W, something like that. In the same way, bias has to be calculated. In the same way, input to hidden weight has to be calculated, and also the bias of input. So those four things has been done here, and in both cases, in all these cases, learning rate is vital, because if you don't have learning rate, means that you are not controlling how speed that the model will learn. So definitely there will be a chance of failure of a good learning, right? Anyway, so this is all about. So once this line is done, it means that now your model is ready with another set of weight to to continue with the data. But as I told you that we are going to store the losses, so that's why I have just stored the loss here, which is nothing but, as you can see, See, here the error is like a squared error basically we are storing, right? And here the epoch value is very high I have kept, okay, and that's why I'm writing that I'm not going to store, I'm not going to print the error value in each and every iteration. Rather, for every 500 epoch I will see what is the error value. That's why I have written this one, that's all, okay. And now once it is done, once the training done, say for example, you read the chapter, say a particular chapter or maybe a particular book, say 10 times. Now I can assume that okay, you are enough matured, enough learned to give exam. So giving exam is nothing but this prediction part. So prediction part means what? Now I will give some unknown input which you have not seen during learning, but it's similar to the thing you have learned. Not exactly, but similar. So you must answer this properly, correctly, right? And that is what the test is. So in during predict function call, what this predict function is doing, predict function is simply giving you the output based on the input that it is receiving and the weight that finally decided after learning. Here there is no weight change part. Once you receive the output, now you can check that how, with the, you already have a data, right? Because you have a test data, you know that based on this test inputs what should be the probable output, and what basically you are doing, you are passing those test inputs to the predict function, and predict function is basically giving another set of output which is a predicted output, and you have the actual output in your hand, so you can easily calculate or map that how much the predicted output is deviating from the actual output, and based on that you can say that your model has some certain level of accuracy, right? So that is what the whole thing is done here. Now you see here what I have done, I have just basically kept the values of x and y from the data set, the data frame, and then I have just applied the some encoding process for the y part, okay. And here you see this part also you have already seen in previous classes, that is I have used a function train test split which is present under scikit-learn package. So if you want to use train test split function, you have to import it from sklearn.model selection. And if you call this function, what this function does, this function will divide your whole dataset into two parts, train data part and test data part. And also it will divide the the inputs and outputs like train x, train y, test x, test y. So these four things the function will return to you, and that's why I have kept these four variables, which is clearly storing those data. X train, X test, X train and Y train for training, X test and Y test for testing. So what I will do, I will definitely use this X train and Y train variable during training and X test and Y test during predicting, right? So that is what I have done here. So I have first of all I have just specified the architecture of my multi-layer perceptron, that what should be the input size of the neuron, input layer neuron, what I'm trying to find out the hidden layer size of the neuron, I mean the number of neuron in the hidden layer, and also the number of neuron in the output layer. See here, I have considered output layer as 3. Why? Because as I told you that instead of taking only one output, you can take multiple outputs representing each and every class. And sometimes it is very, useful. And that's why actually I transform the Y data, the output data, using level encoder, which is basically encoding the data into into n number of levels, right? A level encoder also I have discussed in my previous classes. If you cannot recall, you may go back and you can check that. Anyway, once this architecture is created or architecture is decided, then we can call the, you know, that train function. But definitely train function, predict function, everything present within this class. So I have to create an object, right? It's an object oriented programming type of thing, right? So that's why what I have done here is, see, I have created an object with these inputs, because these inputs has to be there. If you see in the delta function over here, sorry, if you see in the init function, you will see there are three inputs it is passing. Don't think about self. Self is representing, it's the like the current one. Okay, so self cannot be an input. So now see here, once the object is created, so MLP is the object name. With this object name, you can call all the functions. So that's why actually I have done here. You see, so I've called the train function by this MLP.train, where I have passed the data. Okay, X train, Y train, and something like that, and then epoch. I've given 5,000 epoch. That means 5,000 times the data will get revised with learning rate 0.001. Okay, and I'm assuming that maybe after 5,000 times the data will be learned enough by the model, and then I can check how good the model has learned, and maybe I can go for the prediction. I just simply call the predict function, passed the X test, and I got the Y pred value, and then I'm just checking how much Y pred is matching with Y test. Right. And based on that, I'm getting the accuracy, which is representing like this. And then basically I've just plotted it here. So let's do one thing. Let's run this one by one. So I don't require all this. Maybe I can put only head, and if I just run this, yes, it's run. Now I will run this line. Run again. Now I will go to run this one. Done. See, if you print here, I mean, maybe if I go here, and if you print here X train, you will see the data. And also if you print Y train, you will see the data like this. So in which class it is belonging, it is showing. Okay. Anyway, so now let's start. We will just define it and we will train the model, and then we will predict. And during training, whatever accuracy, whatever loss basically we have calculated, that we will get from this MLP.losses, right? Because the losses, if you can recall, a losses was a variable name here, which was a variable of the MLP class. So if this losses variable has the all the losses, so I can check how good, how the loss is actually gradually decreasing. I can see that, right? So if you run this now, and just you see it's quickly doing this, and if you see these epochs, in the first time the loss was 0.98. After 500 times the learning, the loss becomes 0.41. After 1000 learning, it becomes 0.3692. So if you recall the curve of the error during any learning, I told you, like the error curve actually gradually decrease. So it is doing something like this. You see the error is gradually decreasing, right? And maybe if I continue with some more iteration, maybe gradually it will decrease, right? But anyway, This time it is not my goal to make a best model. Just I am showing this code to show you, to give you an idea that how you can write or develop a multi-layered perceptron from scratch without using any predefined function. And anyway, as a result, as you can see here, with the unseen value, it is showing 70% time your data is giving correct result. So if you give 10 data to the model, 7 times it is showing correctly. So it's learned enough. It's a good accuracy, but obviously there is a lot of scope to improve this. And if you see the loss, this loss, this loss looks something like this. So it's a, with respect to epoch, as epoch grow on, the losses started decreasing, and at some point of time you see the rate of change of the loss started decreasing. Rate is not at the same line. Initially the rate was like this, if you see the slope, but at the end the slope is not that level of good. So naturally it happens that after some set of iterations, that may be 1000, in some cases it is 10,000, depends on the problem or the type of architecture you are using, the gradient of the loss gets freezed towards zero. So this is all about the data that basically, all about the code that basically we have written here, just to understand how to develop a MLP model using scratch. I mean from scratch.